Here's another example of being able to solve a differential an initial value problem using a Laplace transform. Again, a first order, just to kind of get our feet wet with this. So we have y prime minus y equals sine of t, where y at 0 is equal to 0. So basically the same problem as before, except now we have a function sine t. So just like we did before, we're going to start by finding the Laplace of y prime minus the Laplace of y is going to be equal to the Laplace of sine t. And then we're going to use our differentiation rule, okay? And you might remember from last time that the derivative of the Laplace, or the Laplace of the derivative, excuse me, is going to be s Laplace of y minus y at 0. And then we also have this minus Laplace of y. And the Laplace of sine, if you look in your table, that's going to be 1 over 1 plus s squared. Now we know that y at 0 is going to be equal to 0, right? So that's going to cancel that out. And then what we can do is we can factor out the Laplace of y. It's almost similar to when you took calculus 1, that in implicit differentiation you solve for y prime, or dy dx, whatever your notation was. Now we're going to solve for ly. And so L of y, or the Laplace of y, times s minus 1 after factoring is going to be equal to 1 over 1 plus s squared. And just like we did in the previous example, we're going to divide by the s minus 1. And so we're going to get this. We're going to get Laplace of y is going to be equal to 1 over 1 plus s squared times s minus 1. And now what we can do is, now that we've solved an algebraic equation and it doesn't have any derivatives in it, as an integral transform generally does, now what we're going to do is we're going to take the inverse Laplace. Okay, so again, it's going to get a little bit ugly. So we're now going to have inverse Laplace of the Laplace is going to be equal to the inverse Laplace of 1 over 1 plus s squared times s minus 1. And now what we have to do is we have to find the partial fraction decomposition of what we have inside of the right-hand side. Now we know the inverse Laplace of the Laplace is just going to be y. So y is going to be equal to the inverse Laplace of 1 over 1 plus s squared times s minus 1. We're going to use our decomposition, so 1 over 1 plus s squared times s minus 1. And when we do the decomposition, notice that we do have a quadratic. And so for our quadratic, remember the numerator has to have 1 less power than the denominator. So it's going to be 1 plus s squared in the denominator, as plus b. And then on the right, to the right of that, we have our linear term. Okay, so this one's a quadratic, and this one's a linear term. So that's going to be c over s minus 1. We're going to multiply through by the common denominator. So we get 1 is going to be equal to as plus b. Now the 1 minus s squared is going to cancel with the 1 minus s squared, and we're going to be left with s minus 1. And then the s minus 1 is going to cancel with the s minus 1, so that's going to be times 1 plus s squared. All right? And just to make it painfully clear as to what I'm doing here, I'm just multiplying all the numerators by 1 plus s squared, s minus 1. All right, so just to make sure we all understand, this cancels with this cancels with this. We have s squared plus 1, and then s minus 1, and so this s squared plus 1 cancels with this one, and that's why we're left with as plus b, s minus 1. And then finally, over here, exact same thing. And so notice the s minus 1s, and we have c s squared plus 1. All right, so just to make sure you all understand where all that algebra is going, we're just multiplying both sides through by a common denominator. We're going to FOIL out the right-hand side, and then we're going to collect like powers, so bear with me as we do this. So now we're going to get 1 is equal to as squared minus as plus bs minus b plus c cs squared. And then if we group all the like s's, or the like powers of s, and we factor them out, let's rewrite the left-hand side as 0s squared plus 0s plus 1. And notice that we have an as squared and a plus cs squared. So that means that a plus c times s squared. Notice that we have a minus as and a plus bs. So we're going to factor out that s, and we're going to have negative a plus b. And then finally, for the last parenthesis, we have a negative b and a positive c. So that means that minus b plus c is going to be equal to our 1. And so now we can get our system. It's not going to be the easiest system we've had. So we're going to have a plus c is equal to 0. We're going to have negative a plus b is equal to 0. Okay, and again, what I'm doing here is coefficient of s squared must be equal to coefficient of s squared. Coefficient of s must be equal to coefficient of s, and then constants must be equal to constants. So we're going to have negative b plus c is going to be equal to 1. And probably the easiest thing to do with this is to probably solve this by using some sort of substitution, right? One of the things that's really cool about this one is that we could solve both of the first equations in terms of a. So, or just for a. So notice that in the first equation we get a is equal to negative c. And then we also get that a is equal to b, which also means that b is equal to negative c as well by transitivity. Right, so those are just some truths that we can find just from those first two equations. Since b is equal to negative c, we can just go through and substitute that back in. So we can just substitute right here and solve. So we're going to get opposite of negative c plus c is equal to 1. Or in other words, 2c is equal to 1, or c is equal to a half. We know that a is equal to negative c, so a is going to be equal to minus 1/2. All right, just bum right here. And then since a is equal to b, we know that b is also equal to minus 1/2. All right, so pretty cool that we could solve this 3x3 system pretty quickly. All right, so remember all the way back up, this was our decomposition. So we have as plus b over 1 plus s squared plus c over s minus 1, and we're just going to plug in for a, b, and c. Remember we had y is equal to the inverse Laplace of all that stuff. So remember we had as, so that's minus 1/2 s plus b minus 1/2 divided by 1 plus s squared, and then plus the inverse Laplace. And remember we had s minus 1 and c, so that's going to be 1/2 over s minus 1. All right? And now that we've gone through and we were able to get our Laplaces, this one we're going to break up. This is a little bit sneaky as to how to do this one. And remember some of our techniques. We have completing the square. We have adding and subtracting a mystery number to the numerator to kind of get it to fit. We have first translation theorem. So inverse Laplaces are sneaky. All right? Here's what I'm going to do. I'm going to go through and I'm going to rewrite this as two separate inverse Laplaces. So I'm going to have minus Laplace of inverse of minus 1/2 s over 1 plus s squared plus inverse Laplace of minus 1/2 over 1 plus s squared. And then finally we have plus Laplace inverse of 1/2 over s minus 1. And what we could do is we can factor out those 1/2s, make this really nice for us. So now y is going to be equal to minus 1/2 inverse Laplace of s over 1 plus s squared plus, or actually minus 1/2, excuse me, of the inverse Laplace of 1 over 1 plus s squared. So sorry I had to squeeze that in there. And then finally we can just say equals 1/2 of, we've actually seen this one before, and it's not an equals, excuse me, of 1 over s as s tends to s minus 1 for our first translation theorem. The good news is the first two of these inverse Laplaces are strictly right from the table. We don't have to do anything from that. And also the good news is that this last one is one that we just saw in the previous example. So for our final answer for this, our y is going to be equal to minus 1/2. This is going to be the cosine of t minus 1/2. The next one is going to be the sine of t. So go into your table, verify this for yourself if you don't believe me. And then finally for the last one, this is going to be, since a is equal to 1, we know that the inverse Laplace of, and this should have an inverse Laplace in front of it, the inverse Laplace of 1 over s is 1. And by the first translation theorem, as this s approaches s minus 1, that's going to be e to the 1t. Right? Or another way to write this is we can factor out a minus 1/2, and we can write this as cos t plus sine t minus 1/2 e to the t, if we chose to do it that way. Lots of different ways we could write it. Excuse me, not minus 1/2, just minus e to the t. So factor error there. Fortunately, I caught it. Okay, so hopefully this is another good example for you all to be able to see how the Laplace transforms work, as well as the inverse Laplaces. Now, in the next two videos, what we're going to do is we're going to take a look at how we solve second-order differentials using our Laplace transforms.